the kind invitation. It's my great pleasure to talk today during this joint colloquium, and I would like to apologize for not being able to join and to talk to you in person, but hopefully in the near future, when the pandemic situation will allow us, I will be able to visit Bologna, and it will be with extreme pleasure. So indeed, today I would like to talk about the evolution of galaxies in a metric as defined by the cosmic web. So the cosmic web is one of the most striking examples of a very prominent geometrical morphology displayed by a physical system, so our universe in this case. But besides being it a very spectacular feature on large scales, such as, for example, seen on the background image in the distribution of matter in one of the cosmological simulations, the question that arises is whether we should care about it at all in the context of galaxy formation and evolution. And well, already such a naive argument as galaxies do not form anywhere suggests we should do so. But let's start from the beginning. So it was this celebrated map of the first CFA redshift slice that provided an initial hint about the existence of the cosmic web. At the time, however, and it was back in 1990s, the redshift slice was so thin that it was not immediately clear what the nature of the observed structures was, whether these were the two-dimensional pancakes or the three-dimensional bubbles seen in the projection or anything else. In forthcoming years, this view expanded dramatically thanks to galaxy redshift surveys such as 2DF, or even in a more spectacular way, SDSS, just to mention a few. So these and many other galaxy redshift surveys have clearly established that galaxies are not randomly distributed in the universe, but are rather located in these dense and compact groups and clusters, in these less dense filaments and walls that themselves surround these vast, almost empty regions that we call voids, all of which are today considered as the main structural components of the cosmic web. On the side of theory, numerical simulations have shown that, in fact, the observed web-like structure seen in our universe can naturally arise through gravitational instability, with the emergent structures growing from these tiny density perturbations that were generated in the primordial universe. These ever larger, more sophisticated numerical experiments have clearly demonstrated that the distribution of matter, such as the one seen in our universe and traced, for example, by the galaxies that we observe, is in fact a typical manifestation of gravitational instability. So the very existence of the cosmic web is in fact the result of the tendency of matter concentrations to collapse and evolve into these anisotropic, elongated, and flattened structures. So on large scales, where the gravity should be the dominant force, its net cumulative impact is encoded in tides and can be decomposed into two parts. So one is this traceless part, which is directly the definition of tidal tensor, and it is this part that will apply the rotation and distortion to forming to galaxies that form. And then there is this trace, or the scalar part, that is directly proportional to the density through the Poisson equation. And it is this scalar part that has been quite extensively studied in the past in the context of galaxy evolution, giving rise to a series of now well-known relations, such as, for example, mass density relation, color or star formation density, or morphology density relations. So while the mass density relation can be explained and understood through the bias mass function in the vicinity of large-scale structures, it is still debated whether this anisotropic large-scale environment is also driving the remaining relations, or put it more general, whether this large-scale anisotropic environment is driving the scalar and spin properties of galaxies. The fact that there is this discussion is not that surprising, and in fact is expected. And this is because these secondary environmental effects need to be first distinguished from the mass and local density effects, which typically dominate. Another reason why the role of the cosmic web in driving the properties of galaxies has only recently started to gain full attention is the recent development of multi-scale algorithms based on the recent advances in the field of computational geometry and topology that allows us today to study the formation of structures on multiple scales. So one of such algorithms is Disperse, that stands for Discrete Persistent Structure Extractor, which is a geometric three-dimensional ridge extractor that is capable of working directly with discrete data sets. So this makes it perfectly well adapted for the astrophysical applications, such as, for example, the catalogs of galaxies from galaxy redshift surveys. So this first allows for scale and parameter 3 coherent identification of three-dimensional structures of the cosmic web, such as voids, walls, filaments, and nodes, as dictated by the large-scale topology. So without going too much into detail, let me show you how it works on examples. So this top figure is showing in white the filamentary network. So these filaments are in fact the set of segments that connect the extrema together, and we can clearly see how these filaments outskirt the individual walls that are shown here with different colors that themselves surround these empty regions that we call voids. So this is probably better seen on this short movie showing the individual walls with different colors at the boundaries of voids. So this is just one example of the extraction of the cosmic web components as directly obtained from the distribution of galaxies in one of the equatorial fields from the GAMA survey. So once we are able to identify individual features, we can define a new metric to characterize the environment of galaxies, the cosmic web metric, into which galaxies can be projected. So the sketch of this framework is shown on this figure. And for every galaxy, we can define a set of distances, for example, the distance to the closest filament, distance to the closest wall or node, or even the curvilinear distances along the filaments toward the node or toward the saddle point. So these distances can then be used as parameters to study and to assess the impact of individual components of the cosmic web on a variety of galaxy properties. So let's start with the filaments and with the one-dimensional transverse gradients. So in this figure, I'm showing the probability distribution function of the distances to the closest filament for galaxies that are split in different stellar mass bins, in red for the highest stellar mass and in the blue for the lowest stellar mass bin. Vertical lines are showing the medians of these distributions. So we can clearly see that more massive galaxies tend to be located closer to the filaments of the cosmic web compared to their lower mass counterparts. So this example is showing the measurement that has been done within the GAMA survey that samples the evolution of galaxies up to redshift of about 0.25. But the similar kind of mass segregation has been consistently measured across basically all major galaxy redshift surveys from SDSS in the local universe up to redshift of about 0.9 as traced by the Cosmos survey. And similarly, this mass segregation has been identified in hydrodynamical cosmological simulations, such as, for example, Horizon AGN. Now, going beyond the stellar mass, we can repeat the similar kind of exercise and compute a PDF of the distances to the closest filament for galaxies, this time split by their color or the star formation activity into passive, shown in red, and the blue in blue showing star forming population with the same underlying mass distribution. Again, we identify a sort of segregation, so this time a color or a star formation type segregation with slightly lower amplitude compared to the previously seen mass segregation, but it stays still statistically significant. So the passive or the red galaxies are preferentially located closer to the core of the filaments compared to the star-forming counterparts. Again, there is sort of a good agreement between the measurement across different redshift up to redshift 0.9 in the 2D thanks to the Cosmos survey. And there is some level of at least qualitative agreement of this measurement also in the hydrodynamical simulations. So the similar mass and color or star formation type segregations have been identified also with respect to the walls, such that more massive or passive galaxies tend to be located closer to the plane of the walls of the cosmic web with respect to the lower mass and star forming counterparts. Again, this is a measurement from GAMA, but qualitatively similar measurement has been obtained recently for the SDSS and also in hydro simulations such as Horizon AGN. So obviously now you can imagine that this kind of analysis can be repeated for whatever quantity you have at your disposition for galaxies. And here I'm showing the recent results from a study in et al. 2021 that performed this kind of analysis on the sample of central galaxies in the SDSS, and they went beyond indeed the mass and SSFR gradients, and they identified the metallicity and H gradients such that centrals at given stellar and halo mass that are closer to nodes, filaments, and walls tend to be more metal rich. They tend to be also older and slightly more alpha enhanced. So far, we have been concerned only with the one-dimensional transverse gradients with respect to the individual cosmic web features. But ideally, what we would like to do is to perform this measurement in 2D or even in 3D. However, for this kind of analysis, at least in the observations, we would need much larger sample of galaxies. But the first attempt toward a sort of two-dimensional approach is depicted on this figure showing the red fraction of galaxies as a function of both distance to the filament shown on x-axis and distance to node coded by different colors. So we immediately see that the fraction of red galaxies depends both on the distance from the filaments and the distance from node. However, the trend is stronger with the distance to node. So for example, at the fixed distance from the filament, the fraction of red galaxies increases as galaxies are getting closer to node. So this reflects the known underlying color density relation that is well known and has been identified in the galaxy groups and cluster studies. However, this gradual increase of the red fraction of galaxies with the decreasing distance from a node suggests that there are some physical processes that operate already on galaxies when these are still outside the virial radius of dark matter halos. Similarly, at the fixed distance from a node, for example, let's focus on this blue line, the red fraction of galaxies increases as galaxies are getting closer to the filament. So now the question that really naturally arises whether we can understand the existence of these different gradients is in some theoretical framework. So the hints are coming from the excursion set theory that has been quite recently revisited by Musso et al. In 2018 by subjecting the excursion set to the vicinity of the filament. So in such a framework, the expectation for the stochastic that are associated to the stochastic variables can be recomputed subject to the presence of tides imposed by the large-scale structure, which is best captured by this geometry of the filament type saddle point. So the result of this calculation, or one example of such a calculation, is shown on this figure. So the saddle point is sitting in the origin, the direction of the filament is upward, and the direction towards void is toward the right. And what are shown here are the different isocontours for density, mass, and accretion rate with darker colors meaning higher values. So without going too much into details, the main takeaway message from this computation and this figure is that all these isocontours, namely the isocontours of density, mass, typical accretion rate, or the formation time, are all distinct, and they are also a function of not only the radial distance from the saddle point, but also the orientation with respect to the filament. So from this model, it directly follows that the tides that are imposed by the presence of the filament lead to the existence of the different gradients and the different isocontours in terms of density, mass, and accretion rate. Now, there is still some stretch to connect these quantities to the observables. So, for example, there is no clear consensus on how to convert the accretion rate of dark matter halos to, for example, the color or star formation rate of galaxies. And this is necessary because this theoretical framework is strictly speaking applicable only to dark matter halos. But one could assume, for example, that higher the accretion rate, stronger the AGN feedback, and therefore stronger the quenching. And if this scaling, which is sort of reasonable, at least for more massive galaxies, holds true, then from this theoretical framework, it directly follows that the color gradients of galaxies should be different from those of density or mass alone. So now moving beyond this framework that is applicable only dark matter halos, I would like to explore and show you some results that we obtained for galaxies. And to do so, I need to move to cosmological hydrodynamical simulations, such as, for example, Horizon AGN. So Horizon AGN is a large-scale hydrodynamical cosmological simulation. It's a state-of-the-art simulation that contains a pretty standard prescription for some of the main baryonic processes, such as star formation or stellar and AGN feedback. But the nice thing about this simulation is that, in fact, it's a suite of simulations where, apart from the reference simulation, Horizon AGN, there is also a simulation, Horizon No AGN, which is run with exactly the same initial conditions and exactly the same prescription for the baryonic physics, with the only difference, which is the absence of the AGN feedback. And so here I'm showing two examples of galaxies at high mass end, on the left-hand side taken from the Horizon AGN simulation, and on the right-hand side, I'm showing the exactly same galaxy, but now in the simulation without the AGN feedback. So we can clearly see here that the AGN feedback is an extremely important ingredient in terms of our ability to reproduce the morphological mix of galaxies, in particular at high stellar mass, to obtain the same morphologies or similar morphologies as observed in our real universe. So let us now explore the three-dimensional structure of the neighborhood of the filament in the frame of the saddle point. So in this frame, the saddle point is sitting at the origin. The z-axis shows the direction of the filament at the saddle point, and the x and y-axis correspond to the major and minor principal axis of the inertia tensor at the saddle point and in the transverse plane. So once we have identified this three-dimensional structure, what we can do is to cut the longitudinal planes containing the saddle point, but also the transverse plane that is perpendicular to the filament at the saddle point, and study the different galaxy properties, and namely the isocontours within these planes for different galaxy properties. So let us start with the galaxy number count. They are here the longitudinal and transverse planes on the top and bottom panels respectively for galaxies from Horizon AGN simulation at redshift 0 at different stellar mass bins. So on the left, it's the lowest stellar mass, in the middle is the intermediate stellar mass, and on the right-hand side, it's a highest stellar mass bin. So immediately we can see that regardless of stellar mass, these isocontours clearly depend not only on radial distance from the saddle point that is sitting here in the origin, but also on the orientation with respect to the filaments that is in this Z direction. So for example, at the fixed radial distance from the saddle point, galaxies are more clustered in the vicinity of the filaments. They are also more clustered in this longitudinal direction near the nodes. So the maxima of these galaxy number counts are shown with these black crosses. So there is also a sort of a stellar mass dependence of these isocontours, meaning that more massive galaxies tend to be more clustered near the filaments and also near the nodes. So as expected, the saddle point is the local maxima of the galaxy number counts in this transverse direction towards the filaments, and is the local minima of the galaxy number counts in the direction along the filaments towards the nodes. Similarly, for the stellar mass isocontours that are shown here for the entire galaxy population, again in the Horizon AGN simulation, we recover again this dependency of the isocontours both on radial distance from the saddle point and on the orientation with respect to the filaments. So again, the saddle point is the local maxima of the stellar mass in this transverse direction towards the filament, and is the local minima of the stellar mass in the longitudinal direction from the saddle point towards the node. So higher stellar mass galaxies tend to be located closer to the filaments compared to the voids, and along the filaments they tend to be located, or higher mass galaxies tend to be located closer to the nodes compared to the saddle points. Now, going beyond the stellar mass isocontours, what is interesting to analyze are the isocontours of the specific star formation rate that are shown on these three longitudinal planes or cross sections, again at different stellar mass bins. So we immediately see that these isocontours are much more complicated, they are much more perturbed, but there is one very interesting feature that is best visible at the highest stellar mass along the filamentary structure. So the saddle point is still the local maxima of the SSFR, again in this transverse direction, but it is the local minima of the specific star formation rate in this direction along the filament. So the SSFR increases along the filaments in the direction toward the node. It reaches a maximum somewhere in between the saddle point and the node, and then it again decreases toward the highest density node and beyond. So we clearly recover the decreasing specific star formation rate with increasing stellar mass. And this is clearly the effect of the AGN feedback. We can check this by comparing these isocontours in the simulation without the AGN feedback. And we see that while at low and intermediate stellar mass, there are no big differences in these isocontours, the situation is dramatically different in the highest stellar mass bin. So including the AGN feedback not only leads to a dramatic decrease in the specific star formation rate of galaxies, but it seems that the AGN feedback is also able to impact the shape of these isocontours, in particular in the vicinity of the highest density node. So these isocontours of the specific star formation rate are fairly similar, qualitatively speaking, to the isocontours of V over sigma, which is the rotation over dispersion dominated velocity. And it can be seen as a proxy for the morphology of galaxies, with high V over sigma, meaning dominantly disk morphologies. And these isocontours are very different from the of the stellar mass that I was showing previously, but also the isocontours of, for example, age. So this suggests that there is some, let's call it a hidden variable that goes beyond the stellar mass that is driving the shape of the isocontours of the properties of galaxies, such as their morphology or specific star formation rate. So what this variable could be? So the obvious candidate is the halo mass. So here I'm showing the longitudinal cross-section of halo mass for the highest stellar mass bin. And we immediately see that these isocontours are very similar to what we have seen for the stellar mass on age. And the similar thing is a similar qualitative behavior of this isocontour is for the local density shown on the second figure. So this suggests that there must be something else that goes beyond the halo mass and the local density that is driving, for example, the morphology of galaxies in this referential frame. So we can check this more quantitatively by defining a mapping, by calibrating directly within the simulation, some sort of mean mapping between the halo mass and the local density on the one side and the V over sigma on the other side. And we can use this mapping to compute the longitudinal isocontours of this map V over sigma and compare it directly with the measurement of this property in the simulation. And what we obtain is this map of residuals. So first of all, we clearly see that these residuals are different from zero, but another interesting feature is that these residuals clearly exhibit a position dependent, or at least a position in the saddle frame dependent discrepancy between the maps of the morphology. So now let me speculate what could be what physical parameter could be responsible for this residual scatter. So it has long been known that the angular momentum stratification built from the anisotropic tides on large scales is a key underlying property driving the morphology of galaxies, which in turn correlates with the star formation activity of galaxies. So it was shown also that galaxies in the vicinity of the large-scale filaments of the cosmic web acquire the angular momentum through cold gas accretion. And galaxies are expected to accrete more efficiently if their angular momentum is aligned with the filamentary structure, which defines the preferred direction of inflow. So it is expected in this picture that as galaxies are forming in the vicinity of these vorticity-rich filaments, they accrete the gas, they accrete it efficiently if their angular momentum is aligned with the filament, and it means that they will increase their V over sigma parameter as they drift towards the node without encountering some significant major merger. Merging with other galaxies changes a little bit the situation. It modifies the orientation of the angular momentum, and it also impacts the morphology of galaxies. So what we suggest, or the interpretation of this result, is that this excess that we see in these residual maps may be a signature of the maximum efficiency of the cold gas accretion. So in this interpretation, it follows that the efficiency of the angular momentum advection is a relevant process. So this brings me to the next topic of my talk, which is the angular momentum of galaxies and halos. So there has been sort of a recent agreement across the measurement within the hydrodynamical cosmological simulations on the orientation of the angular momentum of galaxies with respect to the filaments. And what has been identified and confirmed consistently is this stellar dependent flip of the spin or the angular momentum of galaxies, such that low mass galaxies, shown here with the purple or bluish lines, tend to have their angular momentum aligned with the neighboring filaments, while the more massive galaxies, for example shown here in the red, tend to have their angular momentum in the perpendicular direction. So this agreement is across the different cosmological simulation is very important because the initial measurements that have been done within the Horizon AGN simulations were done with a simulation that is grid-based. And so there was this huge question whether the obtained results are just the consequence of grid locking that is typical for this kind of codes. However, the recent measurements in the SIMBA simulation, which is really a particle-based code, confirm this mass dependence of the spin orientation of the filaments of the galaxies, with respect to the filaments. So you may know that this is consistent with the measurements of the orientation of the angular momentum for halos. So this has been known since some time. So the fact that we measure the similar kind of the angular momentum orientation than the one that is seen for the halos means that the galaxies retain some memory of the large-scale environment from which or within which they were formed. Similar kind of mass-dependent spin flip is also found for the walls of the cosmic web, such that, again, the low-mass galaxies tend to have their angular momentum within the plane of the wall, and the more massive galaxies tend to have their angular momentum in the perpendicular direction of the wall. Again, there is a good agreement in the measurement of this effect across hydrodynamical simulations using very different codes and very different prescription for the baryonic processes. Again, this measurement is consistent with what has been known for halos. Again, even for halos, there is this mass-dependent spin flip. And again, this means that galaxies retain a certain memory of the environment within which they formed. So on the side of observations, let me bring your attention to a recent result done in the IFU survey SAMI that confirmed this mass dependence of the spin flip of galaxies. So this measurement has been done in the 2D using the SAMI data and the cosmic web features extracted from the GAMA surveys. And this measurement confirmed, or this study confirmed, that the low-mass galaxies tend to have their spin aligned with the neighboring filaments, while the massive galaxies tend to have their spin in perpendicular direction. So again, going beyond the stellar mass, a recent study, this time in the IFU survey manga, have shown that there is some signature of the alignment of the based on the morphology of galaxies. So in the sense that the late type galaxies, so the disk or spiral galaxies, tend to have their spin aligned with the neighboring filamentary structure, while the S0 galaxies, so galaxies with some substantial central bulge component, tend to have their angular momentum in the perpendicular direction. So this kind of measurement for S0 galaxies is pretty consistent with the measurement in, for example, SDSS, mass data. However, for the late type galaxies, there is a sort of a disagreement within the literature. So this will have to be confirmed with the future surveys, ideally IFU surveys, for example, such as the future Hector survey. So again, here I would like just to stress that the results from hydrodynamical cosmological simulations are very consistent in terms of stellar mass. However, in these hydrodynamical simulations, when we go beyond the stellar mass, like for example, looking at the morphology or other properties of galaxies, then the results start to diverge. So again, there is some interesting results to be gained and some knowledge to be gained thanks to future observations. So this brings me to the final topic of my talk, which is focused on the nodes of the cosmic web, and namely on the connectivity of the cosmic web. So the connectivity is simply the number of filaments that are connected to the nodes of the cosmic web, or better, connected to the galaxies or halos that are sitting at the nodes of the cosmic web. So this filamentary network represents a very prominent channels of the transport that provide galaxies with not only the angular momentum and mass, but also the cold gas, which is extremely important for the star formation and for the buildup of the morphology of galaxies. And therefore, the connectivity is a natural probe of the growth of the structures, and it is also a very critical ingredient that is driving the assembly history of galaxies. So that is why it is interesting from the point of view of galaxy formation and evolution to look at the tracers of the connectivity of the cosmic web on the properties of galaxies. So for the remainder of this talk, I will show you a few results on the connectivity of the nodes using the results from hydrodynamical simulations such as SIMBA, but also Horizon AGN. And I will compare these results from the result obtained directly in the observations, namely the SDSS, that is shown, one slice from this survey is shown here with the identified filaments shown in gray. So the easiest thing one can do is to measure the histogram or the probability distribution function of the connectivity of the filaments. This is shown in blue with the blue lines, solid for the SDSS and dashed and dotted for the two hydrodynamical simulations, namely AGN and SIMBA. So these distributions are in a really good agreement. This vertical arrow is showing the median of this distribution. So for all three data sets, it is 3. And also the mean connectivity throughout these three data set is equally close to 3. So on average, the galaxies are connected to 3 filaments. However, the connectivity is a function of the stellar mass, as shown on this right-hand side plot. And we clearly see that higher mass galaxies tend to have higher connectivity compared to their lower mass counterparts. Again, there is a very good qualitative agreement between the data, so the SDSS shown with these gray lines, with hydrodynamical simulations shown with these colored lines. This additional offset is simply driven by the difference in the density distribution of galaxies in these data sets. Once we account for this in a way, the agreement is even better. So let's now focus on this dependence of the connectivity on the stellar mass in the SDSS as a function of different galaxy properties. So here I'm showing the connectivity as a function of stellar mass for 2 different samples of galaxies in the SDSS data, in red shown for passive galaxies and in blue shown for star-forming galaxies. So we clearly see that at fixed stellar mass, passive galaxies tend to have higher connectivity compared to their star-forming counterparts. Now, to go beyond the known correlation between the specific star formation rate and the stellar mass, what we can do is to compute these residuals of the specific star formation rate, which is basically the difference of the specific star formation rate of a given galaxy with respect to the mean SSFR at the given stellar mass. And this quantity is shown on x-axis. And again, for the entire population of galaxies in gray. And we can clearly see that there is a dependence of the connectivity on this residual SSFR, such that galaxies that have a higher deficit of specific star formation rate have higher connectivity compared to the galaxies with the excess of the specific star formation rate that have lower connectivity. So what is interesting that when splitting the population of galaxies again into passive shown in red and star forming shown in blue, at the fixed SSFR residuals, we still recover that the passive galaxies tend to have higher connectivity compared to their star forming counterparts. We can repeat this exercise now by splitting galaxies by their morphologies for ellipticals shown here in red and the spirals or regulars shown in blue. And again, at fixed stellar mass, we see a clear difference in terms of connectivity such that ellipticals or S0 galaxies tend to have slightly higher connectivity compared to the spiral galaxies of the same stellar mass. And again, similarly to what I have been explaining previously, we can repeat this measurement with the SSFR residuals to go beyond the underlying SSFR stellar mass relation. And we obtain the same result as previously, namely that even at fixed residuals of the specific star formation rate, there is a clear difference in the connectivity for different morphological types, such that the ellipticals have higher connectivity compared to the spiral galaxies at the fixed offset of their SSFR at the given stellar mass. So now what about the measurements from the hydrodynamical cosmological simulation? So I'm here showing just an example from Horizon AGN and just for the specific star formation rate, but we obtained a very consistent result in the SIMBA as well and for the morphology as well. So as you can see, there is a very good qualitative agreement between the data in the observations and hydrodynamical simulations. So now let us rephrase this result in terms of underlying physical properties, in terms of distinguish or to say something about the difference between the halo mass and the environment, in this case parameterized by the connectivity. So that's what is shown on this plot, where I'm showing the connectivity as a function of halo mass of galaxies, split in according to three different galaxy properties: the stellar mass on the left-hand side, specific star formation rate in the middle, and the V over sigma, or the proxy for morphology, on the right-hand side. The gray line in each panel is showing the connectivity as a function of halo mass of galaxies for the entire population. So we clearly see that galaxies that are living in more massive halos tend to have higher connectivity compared to the galaxies living in a lower mass halos. And what is interesting is that at fixed halo mass, we see that, or we find that the connectivity, the galaxies that have higher connectivity tend to be more massive, tend to have a lower specific star formation rate, and tend to have a lower V over sigma, so they tend to be more elliptical, elliptical morphology, compared to the galaxies with lower connectivity at the same halo mass. So this is interesting because naively, at least at high redshift, one would expect that the higher connectivity means more accreted material, which translates into higher stellar mass and higher star formation rate. However, this measurement that I'm showing is done at redshift 0, and it's not obvious to guess what is the impact of the connectivity at a low redshift. And this is because at low redshift, it's not obvious that all the filaments that are connected to the dark matter halos can easily penetrate inside to the interior of these halos towards the galaxy. So this is one point. And the second one is that at low redshift, the major merger are less frequent, and they also be drier, meaning that they are bringing less gas that can be available for, let's say, star formation or for rebuild up of the disk morphology. So, and indeed we obtain exactly the opposite, namely that at low redshift, the higher connectivity at fixed halo mass means a lower specific star formation rate. So now we can compare these results with the result obtained in the simulation without the AGN feedback. This is shown on the top panels. And what we see is that while at the low halo mass end, there is a good agreement between, or there is no significant difference within the error bars between the different galaxy properties. However, for example, at high halo mass, the connectivity of massive galaxies is significantly higher compared to the connectivity of lower mass galaxies. And this could be the signature of the past effect of connectivity in the buildup of the stellar mass through the gas accretion. And we don't see this effect for the specific star formation rate because the specific star formation rate, which is more instantaneous quantity, is also impacted by other quenching processes, such as, for example, gas shock heating that can overcome the positive effect of the connectivity. So in this framework, or in this global picture, the dispersion of different galaxy properties at fixed halo mass is driven by the connectivity of the cosmic web, but the exact ordering of these quantities is clearly driven by the AGN feedback. So now this brings me to the conclusion of my talk. So in the first part, I presented a series of segregation measured across the different redshift and different galaxy surveys from the SDSS through GAMA up to redshift 0.9 in the Cosmos survey. And I was talking about this mass segregation, color or star formation rate segregation, but also age and the metallicity segregation with respect to the filaments, but also this preferential alignment of the angular momentum of galaxies with respect to the filaments at low mass and the preferential perpendicular orientation at high mass end, or for late type galaxies and the S0 galaxies in different surveys. Similar segregation has been identified also with respect to the walls. And a few takeaway messages from the results from the referential frame of the saddle point is that the specific star formation rate and the morphology of galaxies clearly show a dependence beyond the mass and the density. And these residuals are clearly tracing the geometry of this saddle point. On the side of the connectivity, let me just bring your attention to the fact that connectivity is a very practical observational proxy for past and present accretion, including obviously the minor mergers and also the diffuse info. So I would like to thank you for your attention, and I'm happy to take your questions.